So we're going to talk about wireless network security a little more. Earlier we had talked about when someone gets into your org through piggybacking or something like that, and then they can get in and jack into the wireless jacks in your network, and usually they can get access unless you're employing something like network access control to prevent that kind of thing. So now we're going to talk about that with wireless security a little bit here. So we have 802.1. whatever. We're going to talk about these protocols here in a few minutes that are going to be on the test as well. But 802.1x, so 802.11 and the other versions as well. Port-based network authentication. So port-based network authentication. And this is facilitated by EAP over LAN, so extensible authentication protocol over LAN, and that's how it's done. So the PNAC, port-based network access control, is implemented with EAP over the LAN. So that's how it works with wireless, is through EAP and LEAP. So we'll talk about that later. MAC authentication bypass is not safe to implement. So if you're trying to do MAC authentication, I'm only going to allow this MAC and this MAC and this MAC. That's not safe because I can listen through the raw packets with something like Kismet and then spoof your MAC. So I can say, hey, my MAC is your MAC, and then I can connect and do anything I want to do. This is a problem hotels used to use. And so for things like Black Hat and DEF CON, those hotels had all kinds of problems with MAC bypass. So the MAC addresses may be sniffed off the wire and reused, thus bypassing the authentication. So network access control, NAC. We talked about this earlier. Security approach that attempts to combine user or system authentication, network security, enforcement, and endpoint security like antivirus, HIP, vulnerability assessments, things of that nature, and also disk encryption. The HIP, by the way, is host intrusion prevention. So the parts of authentication for 802.x authentication involves three things: the supplicant, the authenticator, and the authentication server. So if we take a look at this little diagram over on the bottom left there, we have the supplicant, which is a person trying to authenticate, and they're using the EAP protocol to talk to the authenticator. And then after that, they hit the radius or diameter server, which by the way is a test question, radius and diameter server, and then that talks to the authentication server itself, and then a decision is made out of that. So you have the supplicant, the authenticator, and the authentication server. So where is the radius diameter server in this conversation? It's between the authenticator and the authentication server. So the radius and diameter servers are involved in the port-based network access control, or network access control for wireless. What type of a server do you need? A radius or diameter server? I believe that's the test question. So WPA2 uses AES 128 CCMP for encryption. So here's a question. WPA2 uses AES for wireless data encryption. At which of the following encryption levels? 128-bit and CCMP. That's the answer. 128-bit and CCMP. If you're going to be doing this kind of work, if you're going to be writing code for this kind of thing, obviously you're going to need a deep dive in here and understand these a little bit more. But when you see these out in the wild, just remember they're related to WPA2 and wireless encryption. So packet structure with respect to wireless network security. We have management, control, and data. Management packets are packets used to establish connectivity between hosts at layer 2. The subtypes include authentication, association, and beacon packets. So what's the difference between authentication and association? So association occurs first. I say, hey, I want to connect to this wireless network, and then I'm prompted for a password. That's an association. I'm associated to this wireless access point, but I'm not authenticated yet. Earlier, I referred to a wireless router, the Roman Hunter project, which is a wireless honeypot that uses Python scripts to scrape the routers. You can use them on any router you want. It's a neat little project. Again, the idea is not that revelational, but how you do it is kind of useful to security engineers, because the methodology can be applied to anything, and you can scrape anything and gather all kinds of logical information that didn't come canned in your product. So it's kind of useful. You can correlate it with logs. You can do all kinds of very powerful things with it. It's called Roman Hunter, and it's on GitHub and SourceForge. So you'll see in there in the code that you form an association by trying to connect to a router. You're prompted for a password, and you either guess it successfully or not. If you guess it successfully, then you're authenticated. So, but as soon as you're associated, that thing can capture your MAC. So that's how Roman Hunter works. It captures associations, not authentications. Well, actually, it'll capture an authentication too, because the wireless honeypot should never be connected to. So anyone that's authenticated has successfully cracked that network, and now you know you've got a successful attack. So now that MAC address that was authenticated needs to be hunted for on adjacent networks, because that's a rogue MAC an attacker. So that's kind of how the Roman Hunter works. But the associations are people that tried to guess the password. So you may also look for those on parallel networks and dig into them a little deeper. So control packets, they allow for delivery of management and data packets and are concerned with congestion management. Subtypes include RTS and CTS, request to send and cleared to send. Data packets, these contain the actual data and are the only packet type that can be forwarded from the wireless network to the wired network. So this is a sniffing concern. In wireless network, you can't sniff control and management packets. You can only sniff data packets. They're the only ones that are forwarded to the wired network. So if you want to keep an eye on what's going on with your management and control, you have to do that on the device itself. Or you might be able to do it through the raw packets and things of that nature, depending on what it is you're trying to see. So just be aware of that. The management and control packets are not logged. And remember what I said earlier about sniffing? A lot of the management protocols are not sniffed, even on the wired network. It's not because the wired network doesn't see them, it's because the packet sniffers aren't designed to sniff those packets. So that we talked about, you may have to write your own packet sniffer for that kind of thing, or buy a more expensive one that's specifically designed to sniff the management protocols as well. So what is OFDM? It's a frequency division multiplexing. So FDM scheme, frequency division multiplexing, used as a digital multi-carrier modulation method. A large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. So just know that's what it is for the test. It's a frequency division multiplexing scheme. And it's used in wireless security. Orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. So it's how they divide it up and get more information transferred on a busy, noisy network. They can kind of do a little less here, a little more here. Whichever one's good, it uses those data streams. What is a rogue access point? You're going to see this on the test. A rogue access point is standing up an access point with the same name as the ESSID under attack, but without encryption. These devices will still connect and will transmit the password. Okay, well, what does that mean? So say you go to company X and you stand up your computer and you look for wireless networks and you see one named Charlie. So then you create an access point called Charlie with a stronger signal than Charlie's. So there's ways to do that. You can use Ubiquiti Networks gear, you can use the Alpha cards, they all have stronger transmission power. In the realm of RF, the strongest signal gets the connection. So if I have one that's transmitting at 400 milliwatts and I stand one up that's transmitting at 600 milliwatts, everyone will connect to this one unless they're extremely close to this guy. So it's all about proximity. Whoever's closer to the access point is going to get the strongest signal. But in the case where this one's 1,000 milliwatts and this one's only, say, 400, which is a typical desktop device, and here's the laptop. Even though the laptop's relatively close to this 400 milliwatt, the 600 or 1,000 milliwatt may actually get the connection just because of the sheer amount of power. He's overwhelming, this guy. So that's how those things work. Okay, now what is this rogue access point talking about? So the problem with a rogue access point, and say I stood up the 1,000 milliwatt and we have the 400 milliwatt, this is the real one, but I stood up the fake one. But this one does not implore security. So your device, because they're the same name, will still try to connect to this guy. The MAC addresses are different, but they're the same name. So then what will happen is you'll connect to here and you still transmit your password. So now I can get your password that you tried to connect to that device with. So that's the problem with rogue access points. And not only that, but then I can funnel you back to whatever network connection I want and sniff all the traffic traversing that box. So there's a lot of danger with rogue access points. There's a lot of network tools out there that will sniff these things out and determine them as soon as they're stood up, they can be detected because the MAC addresses are foreign.